All right. Sick. All right, we can get started then. I assume everyone here is signed in. If you haven't, then please sign in online. Please do the same if you could. Just because like
How would we sign in online?
you just scan it with your. Oh, are you on your computer or on your phone?
Oh, yeah, I get it. Sorry.
Yeah.
I was thinking like a sign in form, like paper.
No, no, no. Yeah. So yeah, let me know when you're done with that, and then we can move on. But yeah, like Micron wants us to start taking more polls of like who's coming.
Yeah, like more demographic.
Yeah, I mean they're fine with it right now, but as we like keep going,
Can I get a picture of this lecture?
sure.
I did sign in twice. I didn't realize.
That's it's like
Every club does that.
yeah, but you know, they want like demographics too, like who's male, who's female, who's what ethnicity. I didn't ask ethnicity yet, just because like yeah, whatever. All right, anyway. Sure. All right, I'm gonna move on now. I think that's plenty of time. All right, so today we're gonna talk about, let me get this out of the way. What you're gonna be making over the summer. So if you join the summer device processing lab, generally what we're making, we talked about it a few weeks ago, but in case you missed it, and we'll go a little more in depth today. And we'll talk a little on the basics of semiconductors, so the conductivity equation, N versus P-type doping. And then we'll also talk about the main processing steps for devices. So over the summer, you're going to be making capacitors, specifically MOS caps. So MOS stands for metal oxide semiconductor. Capacitors are dielectric ceramics with high relative permittivity. Dielectric materials are insulators that can be polarized by an electric field. That's sort of their definition. This is what polarization looks like on the right side. So you have your two plates and then positive and negative. So electric field is generated and then you get positive and negatives depending on the charge associated with the particles or yeah. So the electric field charges do not flow through the material. So we have this dielectric material in the middle. Instead, the electric charges are displaced from equilibrium positions, leading to the spatial separation of positive and negative charges. This is how we're going to store the electrical energy. So that's the point of capacitors, that we can store it so that when you remove the voltage, you can still have current flowing. Capacitance is quantified with the following formulas. So you have C for capacitance is equal to charge over voltage, which is also equal to relative permittivity times permittivity of vacuum times area over D, and D is the distance between the plates, or just the thickness of this dielectric material. So if you have just a vacuum, it would just be the space in between the plates. But since we have a material here, you can call it the thickness of that material. Anyone can stop me, by the way. This is a pretty informal thing. So if you have any questions, just like shout at me. All right, more on capacitors. We have the dielectric constant, which is slightly different from, if I go back, the relative permittivity. Sometimes it's used, I notice in my classes, it's kind of like used synonymously with like dielectric constant, which is this kappa, but it's not quite the same. So kappa is epsilon over epsilon naught. Epsilon naught, or just epsilon is the permittivity of the substance that we have, whereas epsilon R was the relative permittivity of that particular material. So MOS caps stands for metal oxide semiconductor capacitors. And so in the summer lab, you're going to begin with a silicon wafer, and your insulating material, which is the capacitor, or the insulating material, so that dielectric is the oxide layer that you grow on top of that wafer. And so you have this oxide here. And so you can kind of see it's similar setup, except we flipped it a little bit, and we have the gate and the bulk, or the bottom, whatever you're going to call it. So this is Si over O2 is the oxide. And so it has a dielectric constant around 3.9, meaning it stores electrical energy 3.9 times as well as a vacuum does. And so you might notice that in this diagram, we have this semiconductor and it says P-type. Does anyone know what P-type means for the semiconductor in this image?
Sorry.
No, sorry, what were you going to say?
Is it the doping?
Yeah, exactly. Do you know what type of dopant would give you a P-type? Not necessarily like an example, but like what category broadly? Anyone else? You can guess. I think I know you know stuff.
Positive charge carrier.
Yeah, so you'd have a hole, so which is basically the absence of an electron as a charge carrier. But how do you get that to be the charge carrier? Like, what do you dope it with? So say we have silicon, right, which has valence 4 valence electrons. How would you get a p-type, meaning you have a positive charge associated with it as a charge carrier?
So something with less valence electrons, so it's to the left of it on the.
Right. Yeah. Exactly. So a common p-type dopant would be boron, because boron has 3 atoms. So if you see the periodic table, you'd see like boron, then silicon, then like phosphorus. So for p-type, you get boron because it has 1 less valence electron than silicon. So a semiconductor is basically a material with a band gap energy between that of a that of a conductor, or just a metal, and an insulator. So these are the band diagrams of a conductor and an insulator. You can see for the conductor that we have an overlap between the valence band and the conduction band, meaning that conduction is very easy to, it just happens, like it's kind of just a natural thing. That's why metals are such good conductors. Whereas for an insulator, you have this huge gap between the valence and conduction band. So you need a lot of energy in order to get the electrons to be conductive and, conduct electricity. So charge carriers in semiconductors can be either electrons, which carry negative charge, or holes, which carry positive charge. Holes are sometimes referred to as quasi-particles. Does anyone know why it's called, like what a quasi-particle means?
It's not like a real particle.
Kind of, yeah. It doesn't exist in isolation.
It's a,
It needs to, sorry, what?
yeah, it exists in relation.
Yeah, exactly. When there's nothing else there, that can't be a hole. It's like a metaphysical paradox. It's like, whatever.
So they like to give the chair example, like
What's the chair? Oh,
where,
could you explain?
pretend everybody in the room is electrons
Uh-huh.
and we occupy chairs, which are considered holes. So if we're leaving the chair, then it's like, like an
Yeah,
empty
spot.
chair is a
Yeah.
hole.
I got you. Yeah, I don't know if I've ever heard that one like directly.
The blue LED for tasting video or something. I've never seen that one actually.
All right, so now we can get into intrinsic versus extrinsic semiconductors. So an intrinsic semiconductor is pure crystalline structure and with no impurities. So we're just talking about doping, which is when you add impurities on purpose to a material like silicon. And the intrinsic, your number of electrons equals your number of holes, because as the if I go back real quick, or forward, so I'll just use the insulator because the band diagram is similar to the semiconductor, except that band gap just smaller. Every electron that leaves the valence band and goes to conduction, it leaves behind a hole in the valence, and you have that now electron in the conduction. And so they're equal numbers. So as more keep going up to the conduction band, you get equal numbers still, even though more keep moving. So electrons are going to equal to holes for intrinsic semiconductors, which is represented. Let me move these. So for this one, we kind of simplified the equation. So in the first one, we have N and P. So N is the number of holes, P is the number of, N is the number of electrons, P is the number of holes. And so we can just represent that as N sub I to represent both since they're equal. And so you sort of just do a little bit of algebraic, put it in parentheses and keep the rest, because the Q is also the same, just the charge of 1 electron. And so intrinsic semiconductors also have a low electrical conductivity, especially compared to extrinsic, and also they're temperature dependent. And now extrinsic semiconductors is what we were talking about earlier when you add impurities on purpose. And so that makes, because of the impurities, you now don't have the equality of electrons to holes. There's a difference in number. And so one will become the majority charge carrier and the other one will become the minority charge carrier. They're still contributing to the overall conductivity, but one tends to dominate. And that's what's seen in this extrinsic semiconductor equation. In case you didn't know, this sigma is for conductivity, and it's inversely proportional to resistivity. And so when you solve for this is the conductivity equation, and N is much smaller than P when we have a P-type because we have way more P. It's like usually the values are like 10 to the 18th or something versus 10 to the 3. And so the 18 just completely dominates the 10 to the 3 of N. And so we can just basically say that conductivity is equal to just the P contribution. So can anyone guess what the equation for an N-type semiconductor would be?
The reverse NQ. mu.
Yeah, mu of E, yeah, exactly. It's not mu of H, it's gonna be, so mu is in case you didn't see, it's the mobility. Which has this kind of odd unit of meter squared per volt second. Yeah, and so extrinsic semiconductor also has higher electrical conductivity, and it's temperature dependent and dopant dependent, obviously because there's now dopants. Bruh. It'll come back.
So can I ask you a question?
Yeah, please.
All these things seem like, are they all material specific constants that are known?
Which,
Like electron mobility, like,
Yeah.
It depends on.
Material.
somebody's already calculated this.
oh yeah, yeah, it is temperature dependent also. We don't kind of go into all there's a ton of equations on, and then you get to like density of states, and there's a bunch, I remember all this. I mean, I'm taking a class on it right now.
Right.
Yes.
But the electron mobility, we don't have the sulfur.
Pretty,
Usually it would be given to you if you're given a problem.
yeah, you will be given
Or
a problem.
Yeah, a lot of them have
Look
like.
it up.
No, that's what I'm saying.
Yeah.
There exists such a thing.
Yeah, it's calculated for like, or you can calculate, if you have some weird temperature that you're working at, you can calculate it with you just plug and chug, and it's pretty straightforward. Yeah, does anyone else have any questions before we move on to the next part, which we're just gonna talk more on now N-type. So for the band diagram, remember what an insulator looked like. It was basically this gap, this same gap here on the left, but it was very big. And so for a semiconductor, we just made it a little bit smaller. And so you can see, does anyone know what a Fermi energy level is?
It's
Well, I know he knows pretty much, so we can go for
the
it.
Fermi energy level.
Yeah.
It's the, I remember doing it, but. It's like a theoretical level that the energy barrier gap they have to like overcome. The electrons have to overcome to like jump the top.
Not quite.
Okay.
Man,
Can I hazard a guess?
yes.
Is it like where half the probability, like there's something with probabilities where, the probability of having an electron, like, I don't know.
Like, kinda, do you know?
It's been a while, but is it just like basically the EI line after you add the dopant, that's the line that changes?
So yeah, it does change with dopant, but I'm just generally, what is the Fermi level? Because yeah, it does change. It depends on the dopant, also temperature dependent also, but
So it's like an average of where.
It's
average energy.
it's close, because you get it, it's close. It's the highest possible energy level that an electron can have at 0 Kelvin.
Mm.
So for an intrinsic, it's right in the middle of the valence and the conduction band. And as you go, it moves in one direction or the other. So in this case, we're doing an N-type. And so so you can see this diagram here, this green is the added impurity. So say this is phosphorus, it has this extra electron. And so this extra electron and all the combination, or all the however many donor atoms you decide to add, you get that many states available. So then oh my gosh, that's so annoying. Oh, okay, yeah, cool. So now we have this Fermi energy now closer to the conduction band. And so that's called a donor. It's called a donor state. So since we call the N-type dopant donors, they offer donor states because they have the extra electron, which donates electrons. So this can, wow, you still can't see it. That's crazy. Just gonna have to keep, maybe there's a way, like a particular angle that it likes. Or, no, okay. Please. Sure. Hope it doesn't mess up the Zoom meeting. Yes. Okay. Does anyone have questions on this? Because this is a pretty important concept in semiconductors in general. Anyone have a question on
Anyone have a question on the diagram?
The donor state, the Fermi level,
So
shifting up.
in like just a conductor, would the Fermi level also be at EI right in the middle? I guess it doesn't really matter where it is, or,
So for conductor, the valence and the conduction band are overlapping.
yeah,
So you have Fermi level,
still in between. it,
but they overlap, yeah.
But it overlaps.
It overlaps, so it's still gonna be able to conduct at 0 Kelvin. If you have if you have 0 Kelvin for an intrinsic or an N-type, you still have no conduction because they're not, they're higher, but they're above the valence, but they're still not in the conduction, meaning they're not contributing to the conductivity. Any questions? Yeah.
So what does the N type bring up the Fermi energy?
So the donor atoms, they supply those donor states, which are closer to the conduction band. It just has to do with the property of that extra electron. We can compare it to holes in a second, or I guess now. These holes offer an acceptor state. So instead of being at the top, close to the conduction, it's close to the valence band. It just has to do with the property of the donor atoms. Yeah.
So like, what is the significance of this Fermi energy? Is it like a probability distribution? If there's more, if there's a impurity, the positive one, it would make it such that it was more likely that it'd be higher? I'm not seeing the,
I feel
what's
like,
what's the
yeah,
importance of this?
the probability, like, it shifts the distribution of the probabilities probably.
I guess I mean, it does have to do with probability, kind of. I remember it being like you use Fermi-Dirac versus Maxwell-Boltzmann statistics.
Okay.
That's kind of getting farther than I want to go today. But like if you want to read a little more on Fermi energy, I would recommend it.
But basically the electrons move the Fermi level up and then the
Yeah.
holes move it down.
Yeah,
What is,
yeah.
what is the Fermi level doing for the conductor? Practically.
Practically, doesn't, it just means how conductive
Like,
basically
it just
it
makes
can
it
be.
more conductive.
Yeah,
So, like,
higher
What's the question, if you don't mind me asking?
A diode that like
The-
only conducts in one way or something.
The question was, what's the significance of the Fermi energy when contributing to conductivity?
Got it.
Yeah, so we're, Oh, yeah. yeah, and there is a direct relationship, right? Yeah, okay, I'll move on a little bit now, just so we can not be here too long. So, okay, as we were saying, P-type, there are now holes which offer an acceptor level, which is closer to the valence band. And so, yeah, that's kind of the gist of the P-type. It's exactly the same as the N-type, except you bring it down instead. Any more questions on this P-type instead of N-type? You have a +3, which is missing a hole.
Why is that closer to the balance band, the holes?
It's just, again, it's kind of like the inverse of just like, yeah.
For the same carrier concentration in P and N-type, which one would have more conductivity?
The same concentration?
Yeah.
Like you dope both
Yeah, they're both the same.
into the same,
Should be-
N equals. You have to, so if we look at the connectivity equation, if N is equal to. So you're saying like you don't, you have N acceptors, whatever, like 10 to the 18th, and then you have N donor
Mhm.
is 10 to the
But two
18th.
different
materials.
Yeah, yeah,
samples.
yeah.
Maybe same like in silicon, let's just say.
I-
each of silicon.
Want to say that you just, or, so say you have whatever acceptors would be, boron atoms, and then you'd have phosphorus for a donor. That's almost like treating it like an intrinsic semiconductor, right? Because then this is equal
They're
to
two
N.
different samples
Oh,
of silicon, but.
Oh.
Thing, one of them has a
one-
lower versus higher Fermi energy, right? So then the negative one should, based on your explanation before, I was led to believe that the negative doped one should have a higher conductivity because its Fermi energy is higher.
It's electrons, not because of that, just because they have a faster mobility.
oh, it's a great point.
Yeah, it's still-
I thought you were
Look at
saying.
it For the,
Yeah, so the question was if you have a sample that is doped with a certain value of N-type doping and this a different sample with the same amount of doping, but it's P-type, which one would have a higher connectivity? And the answer is the N-type one, because holes have a higher mobility. So in this term here, the mu sub E is higher than mu sub
Assuming
H.
everything else about the samples.
Yeah, and actually that just remind, because I literally have values here. You can see that the mobility here, I got this from like a table. So you see the mobility here is greater than the mobility of the hole. So yeah, I thought you were saying if they're doped into the same sample, which one would cut? It's like, yeah, it's like you're basically like back to square one. Okay. So now we have some practice problems. If you guys have a calculator or not, we can work them out together if you want, whatever you guys want to do. So the first one is to find the resistivity of the intrinsic silicon. And so well, I don't know. I want you guys to work on it for a second and then we can talk about it. Or we can talk about like the process for it and then make sure our values match at the end. The second one is a little bit harder than the first one, so we can get this first one done first.
Well,
You can use the relationship of, so we have the connectivity and we know the connectivity is the inverse of resistivity.
no, hey, we lost it. Never ending battle.
Yes.
I don't even know what it is.
Okay. Jesus, I just need to like step really far away from this. I, like breathe near it and it just turns off. Does anyone get a similar value? 340-ish thousand, a little bit under.
Yes.
Second.
If anyone not get that and is confused, don't be shy. Yep. Everyone got it? Okay.
I didn't hear what you said the value should be, but
Yeah, it should be about 330.
Eight-ish.
Yeah, 338,000. Does that sound about
got
right?
it.
Yep. Okay, cool. So now for the second question, we're gonna use this. Hopefully it doesn't turn off because I'm touching anything. Okay. Okay, that's fine. Problem 2 is to use the following relationship, which is this NP equals Ni squared. Use the following relationship to find the concentration of holes, which has units of centimeters to the -3, and electrons in a silicon sample doped with phosphorus concentration of 1 × 10⁻17 centimeters and -3. And a hint is to look at the periodic table because your first step should be determining whether or not this N or P set. Let me know if you have any questions.
It was like the phosphorus concentration.
P?
What is P?
So P is the number of holes. I think it's somewhere. Oh, maybe it is up here. But N is the number of electrons and P is the number of holes. Whenever you see this connectivity equation, or yeah, this one, the N is always gonna be number of holes and P is like negative positive. Do you want to think of oh yeah, N is number of electrons. It's like NP, think of negative positive, positive holes and negative electrons. Does anyone have a value that they got? Is anyone stuck? Wait, would you get? Is it 1,000? Yeah.
I'm stuck on.
Yeah. So the way to go about this is that we have the concentration of phosphorus So I'm just gonna say, I should probably write huge.
Or you could annotate this.
Ooh,
Is it like, he has a call with the?
I'm worried that if I touch, it's gonna do stuff, but okay. Yeah, okay. Yeah, we can do that. I'm just gonna write it up here. Okay, so we have the phosphorus concentration. From the earlier slide, you may have missed it. That might be why it's a little bit challenging to solve it. But basically, we have a number of, so phosphorus, you should, if you look at periodic table, you'll see that it's to the right of it, so it's an N-type uh impurity. And so that's a donor. And so you can say that the number of dopants is this value, 10 to the 17th. This doesn't look terrible. Okay, 10 to the 17th. And then we can say this is effectively the value for N. And so once you solve that, you note Ni from this previous question. So we're basically going to do 10 to the so using Ni, I'm going to say that rearranging the equate. Oh no, it just did it. Okay, it's fine. Okay. So we have 10 to the 10 quantity squared. That's a parentheses. Oh my goodness. So that's basically going to be 10 to the 20th, and then we just divide by this 10 to the 17. So just rearranging that equation at the bottom. And so that's 10 to the third, which is also, oh, what? It's still there, but it's dim. Is it because I'm in annotation mode? Has it been like that the whole time?
It just did it.
Oh, okay. If I go away.
10 to the 10 squared.
Yeah.
10 to the 10 squared.
Where is the 10 to the
It was
10?
from the first
From
question.
the ends of.
So it's using this equation and rearranging it. How can I?
Okay, I see.
It's still visible though. It's kind of.
So,
I don't know why it's big. It's still. Yeah, it's that one at the bottom. So NP equals N sub I squared. And so we're just basically, we're solving for the number of holes and electrons, which the electrons, if you just know this first step, which is to set the number of donors, which is given equal to N, which I showed in the previous slide. Oh no, it's gonna stay there. Oh boy.
But the
Clues.
material is like
Clear.
2 to the right of the silicon, would be 2 times that, right?
Would you have double the donors?
If it's sulfur, I don't know if that's used.
Sulfur doping. Yeah, do you know
Or it
that?
was-
I think it would. If you have, say, something to the left over by 2, from silicon, so like barium or something, would that be 2 times the concentration, the number of electrons donated? Because now it's 2,
I get it, but
like,
I've never seen that.
it's not
That's like
really
relevant.
done. That's a tough one, like,
I think you kind of like, for actual manufacturing of that, it's kind of close to not done.
yeah,
Impossible, so
yeah.
even when you go to like.
That's what I was, yeah.
They only kind of deviate one left, one right. They don't-
Yeah. Because, yeah, we can talk about comments like semiconductors if we,
Compound?
yeah. But anyway, those are just some questions. Problem 2 is intensely a little bit harder. So like, don't feel bad. Oh, yeah. Let me try and set back so you can see the thing.
The quality shake.
Oh, literally, yes, that's what worked. Okay, cool. Phenomenal. Okay. Does anyone have any questions? Anyone online or no? Okay, cool. So that was kind of a brief introduction to semiconductors, but it doesn't end there. This is just an introduction. So there are a lot of other ideas as like questions were coming up. It's obvious like it incorporates a lot of other concepts that you need to know. And so some of those include quantum mechanics. So you need to know a little bit about wave particle duality, tunneling, and a bunch of other probability equations and stuff. Types of semiconductors. So there's direct semiconductors, indirect semiconductors, wide bandgap. There's even ultra wide bandgap. And they have different applications. There's junctions and contacts. There's different types of those that they behave differently based on what materials you choose. There's different processing techniques and machines, which we'll go over a little bit right now, next up. But so basically, yeah, there's a ton of research opportunities and jobs to fill. because there's just so much to know and there's so much to do with it. So if you're interested, there's a ton of research that can be done even before you start your lab. So okay, now we can go into, I guess not in the way, I can kind of get this.
Also, before you go.
Yes.
Yeah, it's because, so when you put a dopant into like the silicon, it takes a certain amount of energy for the electron to actually leave, like that atom that it forms together.
The work function, right?
Yeah, so that for any element left or right one over is about 40 milli electron volts, which is room temperature. If you go sulfur, it's about 300. And the second electron is 600.
Electric volts
So,
are
yeah.
milli.
So at room temperature, it doesn't help for conduction at all.
Okay, cool. Thank you for that. Okay, so now we're gonna start going to the processing of semiconductors. This is not every single thing taught here is what you're gonna be doing in the lab. It's just a brief overview of like the main things used in the industry. We'll go more in depth Thursday, like pretty in depth. I think Yen is gonna write some slides for like, was it photolithography?
And
Or-
if you do etching, you can do it.
Yeah, that'd be cool. Yeah, okay, so first as I mentioned earlier, you're gonna start with bare silicon. And so there's different types of silicon. You get monocrystalline. I think the phone might disconnected. Maybe not, I don't know. Okay, so you have monocrystalline, which is just a single crystal that extends for the full length of the material. You have a polycrystalline where you have different crystals kind of arranged near each other, and they have amorphous, which is a sort of random arrangement of atoms. And so polycrystalline silicon can be as much as 99.9999% pure, which is what you want in when you're processing your semiconductors. Okay, so for wafer fabrication, the three main areas in wafer fabrication are photolithography, etching, and deposition. I know some of these terms are kind of small here, but this is kind of the overview of the processing that you may see. So the common terms are like front end of the line or front of line and back end of line. So you can see like the top portion, you get the back end and you get front end at the bottom. Leanna knows more about
Yeah.
back end than I do. I know like nothing about it.
Well, we go over mostly the front end.
Yeah, that's-
In, the lab, device processing lab, because we're dealing with the actual devices and then all the interconnects and like the connections leading up to interfacing with the rest of the circuit, like, you know, PCBs or whatever else you're connecting to, it's back end stuff, so.
Yeah.
So I couldn't hear that. Sorry.
Uh,
I'm pretty unfamiliar with backend myself. Is backend essentially just like another layer of an oxide being grown on top of our already completed device in order to help interface and package it?
Well, there's oxide and then there's also metals, and the metals are patterned like within the oxide.
Yeah, I should mention. So we're basically, you do like a photolithography process, and after you're done with your deposition, you then grow another oxide layer on top of that and do it all over again.
The photolithography, then filling in the trenches that you made for the connections, like the interconnects, and then you would basically use a process called chemical mechanical polishing to flatten everything and make it easier for another round of photolithography, and then you would just keep like repeating those steps layer by layer until you, and they also
Yeah,
figure
but
as you go
I'm sorry. I'm just asking, I guess, more specifically about one part of this process. After they're done flattening it, or your surface, do they then just grow another oxide layer on top of it?
um,
Like, I can't see how these layers are labeled, but for instance, after you're done with your quote unquote front end design, do they then use that process that you're talking about to flatten the surface and then they just grow another oxide layer on top of it? Because that's the only way I can imagine that you would even
Yeah.
begin.
It would, probably with like CBD.
yeah, and you were saying maybe like
It seems like he's like interested at the very end, like when you put it into an actual device.
yeah, you're saying like when you put it in actual, are you asking like for like when you're about to put it in a device, how you package that up? Because sometimes they put polymers and stuff to protect it as well. Is that kind of what you're getting at?
No, I was just trying to figure out, like, packaging is like a totally different process in the end.
Yeah. Yeah, no, we're not going to touch on it at all today. We do want to
Yeah.
have lectures on it, like from like Asadi and a bunch of other professors if we can. Um, but yeah, we
What
can.
I
What's
I
up?
guess what I was talking about is like, if you look between the layers labeled front end and back end, are they growing an oxide layer for each one of those, essentially?
I think those are probably, they probably put down some sort of etch stuff like a nitride layer or something to, so that
Insulate
the,
it.
the chemical mechanical polishing will know when to stop.
Okay. Did you hear that?
Okay.
Okay.
I was trying to figure that out because I was like, how in the world would you grow another layer on top of an already made design and still have this work at all?
Yeah, see what you're saying.
Mhm.
All right.
But
So
yeah, it's probably too advanced of a question for this, sorry.
no, it's all right. Yeah, we do want to have some people talk about packaging at some point, but probably not in this semester, but moving forward.
No, but it'll become more clear as we like introduce more of the steps and stuff.
Yeah. Okay, so now for thermal oxidation, we're just gonna grow an oxide layer on top of the polycrystalline silicon wafer. So in case we forgot we got this polycrystalline because it's very pure. And so now we're gonna grow an oxide layer on top of that. As I mentioned earlier, that'll be your insulating material. So it'll have a high dielectric constant, and that's good for capacitors. So there's two types of oxidation. You can do both in the lab, but they have their pros and cons. Wet oxidation uses water vapor, and so the temperatures, they give ranges of like 900 to 1,000, but again, you can kind of pick your temperature. You don't want to go too far, but those are the kind of the general guidelines to start with. And so wet oxidation is faster, but you do get a lower quality oxide layer. And so when you're making your device and you want very good properties from it, you probably want to spend a little extra time and do a dry ox, which uses just oxygen from a tank that we have in there. We also have nitrogen and stuff like that. So
Charts for each of those processes. So
Yeah.
you can
yeah.
pick some anticipated, like they have equations and charts.
Yeah, we have like a chart for a bunch of the steps for the processing. So you kind of fill in certain areas, but it's generally brought out so you're not, growing oxide after you etch or something weird like that, like, whatever. So yeah, that's generally thermal oxidation. Now we can talk about a little bit about photolithography. So we're going to use something called a photoresist. And so this is a coating you're going to put on top of that oxide to pattern new features onto the wafer. And so photoresist is just a UV sensitive polymer. So the lights in the lab are a certain frequency or wavelength or both, so that they don't harden the photoresist because it's UV sensitive. So we have negative photoresist and positive photoresist. And so the negative hardens when it is exposed, and the positive hardens where it's not exposed to the UV light coming from the lamp. And so you're going to put it in this photolithography machine, and you're going to set your exposure time, and there's some calculation to do based on the intensity of that light that day, because it changes with the day. It's a little bit old, the equipment, but you can just do a simple calculation and figure out how long you want to expose it for to get the exact exposure that you want.
Sure it gets through the entire.
Yeah, exactly. Yeah, so negative photoresist offers better adhesion and better ion implant stability. So ion implantation is a later step. And positive photoresist is more expensive and it gives you higher resolution. So those are it's good to know the difference between positive and negative photoresist, especially if you get in an interview or something. They tend to ask that. I got asked that. Yana got asked that. Did you get asked that before? Positive versus negative? I know that I didn't. Yana didn't. Oh.
What if I use negative photoresist? Is there like something like a specific?
Well, I think it depends on your mask too, right? So if you have a certain mask where whatever you're using, you don't, or you do want it to expose, you would use negative, and then whatever, you'd flip the opposite. Yeah.
So are these photo masks like
actual size what's gonna be put onto the chip, or is that like?
Like, is it 1-to-1 or is there some lenses going on? I'm pretty sure that since we're using a contact lithography machine, it's gonna be 1-to-1. Just like the entire wafer gets exposed all at once. So.
Yeah.
I mean, in industry, they have these things called like stepper machines and stuff where they like send it through different lenses and like, then they only expose what they call a portion at a time called a reticle. And so they need to like automate stepping through all of those areas on the wafer. And so it's more than one exposure for that type.
So in order to get the photoresist on your wafer, you're gonna have to spin coat. So there's a spin coater, basically machine with a little piece that spins, and so you put on a chuck, which is this part right here that's actually holding material. There's a vacuum so that it doesn't move when you're spinning it. And you want it very well centered. That's kind of the annoying part with this, because you're doing it manually. You have to center it so that it doesn't wobble when you're rotating it. If it's a little bit off, you'll see it like kind of like hit like more of an ovalish rotation. And so you want perfect, pretty much perfectly circular, so you get a nice even coating.
Pipettes.
Yeah, so you're gonna put bring a pipette of your photoresist and you put it on the wafer. There's a general guideline of how much to put on so that it you get enough. If you put a little extra, it's not a huge deal. You're gonna lose some anyway because it's spinning, and you have a bunch of surrounding area that you'll coat with like aluminum foil so that it doesn't get everywhere. So yeah, you'll allow the photoresist to spread, rapidly ramp up the coater spin speed. And so yeah, you're gonna spin at certain speed. I think like 3,500 RPM will give you, I forgot exactly the like thickness of that photoresist, but there's a little chart right next to the machine so that you know how fast to go based on how.
And also like it depends on the photoresist that you were using.
Right, yeah. And also, yeah, material specific. So yeah. So this is kind of a general idea of why we're doing photolithography. Right, so in this case, we're not going to be making the Si3N4, we're going to be making the silicon dioxide. So we have the silicon substrate, you have the green, in this case, green oxide. You put the photoresist on, and then you expose it to the UV light. Based on your mask, you'll have a pattern, and then you are gonna, after you're gonna etch it so that you get rid of this middle section here, and then you're just left with this, and then you can strip that with a certain solution that strips the photoresist off. And then you're left with a patterned wafer. So okay, good. So now we can get a little bit into etching. Etching will strip the material that is exposed by the photoresist. So again, there's wet versus dry. We have wet etching, which is what we're going to do in the lab. I guess we could do both actually, because we have the etcher, the plasma etcher.
We're mostly using that to just clean.
Yeah, it's for cleaning most. Okay, so the wet etching, you're going to use the buffered oxide etch, which uses hydrofluoric acid. So that's one of the main reasons that like there's a bunch of, you're going to wear a suit so that you're, you don't spill it on your hands or anything. It's very corrosive and it'll destroy your hands.
5% of your, if you get like the hydrofluoric acid on 5% of your body, it's deadly.
Yeah.
So
yeah, so we're gonna use it to etch, and you're gonna put it in this little what is that called again? The fume hood, or just the hood in general. And so yeah, you're gonna etch away your photo material that's exposed by the photoresist. So when you're etching, you don't get a perfectly straight etch. You're gonna cut away a little bit at the bottom of this film. And so that's kind of one of the problems with wet etching, whereas I guess dry etching, you don't have that
it's like
problem.
isotropic.
Yeah, right.
Like it etches in like all directions.
Yeah.
And then the anisotropic, meaning it etches
Yes,
way more in one direction.
Right. Yes.
So what's the downside of dry etching? Is it basically just slower because you can only etch a smaller amount of photoresist at a time, it looks like, or sorry, you'd be etching the film, not the photoresist. I mean, technically both, but you get what I mean. What are the downsides of dry etching? Is it just slower?
I think it's less selective.
Dry
Like,
etching
you
is
can
like-
do, yeah, you can do a lot more with selectivity, like in terms of material selectivity, like. You can,
Uh-huh. Oh, I get it. So if you're doing multiple layers of, like,
Yeah.
multiple films layers, you'd basically have to use wet etching because dry etching would cut through multiple layers at once, so to speak.
reactive ion etching or something.
Yeah, I mean, yeah,
gives it a little
it's a
bit
li- yeah.
of reaction, But
Sometimes in like vents and stuff, you want the and it's
the anisotropic,
Right.
yeah.
Oh, okay, cool. I didn't know that.
Go.
Something that could be selective, so.
Right.
Sorry, I could only hear bits and pieces of that in the end.
Yeah, for MEMS, which is MEMS, sometimes you want anisotropic etching. So in that case, you want dry etching for that one. So that's what, yeah.
But what are the downsides of dry etching? Is it just that it's less selective, so therefore it cuts through too many layers sometimes if you have like a really quote unquote thick sample?
Yeah, I mean,
Or-
it depends. I guess it depends on what structure you're making and what, like, you know,
You'll need to make like the plasma and stuff, which means it takes up like,
energy.
more energy.
yeah,
Whereas like, you just have chemicals and you dip it in the chemicals.
yeah.
So there's that.
Does that kind of answer your question a little bit there?
Kind of. For me, high energy cost is basically no cost, so I'm just like, all right. I mean, like, how much higher is it really?
Yeah, I'm pretty sure it's slower.
What he's saying is correct, right? It can go through too many layers. So
Yeah.
When you etch silicon dioxide in the lab this summer, you do wet etch because it won't go through the silicon.
Right.
But if you're
Oh,
doing
okay.
dry etch, it will go through both.
Oh, okay. Yeah. So yeah, dry.
Okay.
Yeah, I guess. Yeah, you heard that then.
Yeah, it's too penetrative or
Yeah.
penetrative, I meant to say.
Yes. It. Yeah. Discriminatory. I guess.
Mm-hmm. All
All
right.
right.
Thank you.
Yeah, no problem. All right. So now we can talk about doping. So in this. Yeah. What's up?
What keeps it from eating away at, too much of the film layer?
So you're talking about the wet etching.
The etching,
Yeah. It's
the chemistry.
Yeah, it's just chemistry of it. So like if HCl and silicon, like they just won't eat it. It'll eat away at like that's kind of why they chose this particular HF as opposed to like maybe some other like sulfuric acid or something that'll just demolish everything.
But the little like divots in the film, those never get like too deep where it.
They-
Well, they can, if
they
you
can
let
get
it
you.
etch for long enough, it will just keep.
But yeah, it's not etching in the substrate.
But since there's no more of that film on the sides there, it's just gonna keep undercutting more and more. And eventually, I guess the photoresist will pop off if you etch too long.
Okay, so for ion implantation, this is how we're gonna add the ions to the wafer. So we can create the N-type and P-type wafers that we discussed earlier. So some advantages against diffusion, because there are diffusion techniques also like chemical and physical vapor deposition. So we have a uniform doping concentration. We have more directional control since we're, we can select exactly where we're blasting these ions. Lower temperature process, it's easy production of shallow layers, and you get better resolution. Does anyone have any questions on ion implantation?
We have a machine that does it.
Yes. What's up?
Well, we're not gonna be doing this in. the
Oh, yeah,
lab,
no, yeah,
but if you
Doing
wanna
TBD
do,
and
like, in a later year, when you have a little more experience,
like
then,
MOSFETs, maybe? Do you need this?
You
for
would
MOSFETs?
need something like,
Makes
a
sense.
way
For
to
the
dope.
gate or yeah.
The fusion, the one,
Yeah, source and drains.
the vapor one, it was like you could see in the little hole and you stick it on the top.
Yeah, you got
So I think they do some sort of spin-on, like, spin-on dopant, and so then they just put that in the furnace, and then.
Oh, and then
mix
they
it,
diffuses.
And then it diffuses.
We have that. That's my kinetics project right now for atomics. Yeah, we have to like program it in MATLAB. It's kind of cool. My
So
group.
that is available to us,
Yeah. So
but The ion implantation
I believe
is,
this is what you're just talking about.
yeah, it's interesting because like depending on the
Oh.
amount of energy that you give these ions can change like what happens to the material. So like
Right.
implantation is like the max energy. Like
Right,
you're
yeah, you just blast it. Yeah.
bombarding, so it goes like into the material, but you could also like give it less energy and then it would be more like sputtering. So
Right.
it could knock off material.
Yeah, how are we doing that time?
Uh,
We'll stick-
Okay, what's up?
Yeah, I was just gonna ask, would the ions in this case just be something like phosphorus gas for the doping?
I think
Just that as an example for what kind of ions we'd be using.
isn't
Yeah,
it?
phosphorus or boron.
Yeah, phosphors are like, the dopants that we were talking about.
Yeah, I
earlier.
know. I just wanted to make sure that
Yeah, yeah.
I was on the same page.
Yeah.
And then
Um,
it causes a lot of damage, as you can see in that middle part. And then, you have to do some sort of heat treatment called annealing, where you just have to heat it up and then allow for all of the atoms to kind of settle, like the stress to
diffuse.
diffuse
Yeah.
throughout the lattice, like even itself out.
Yep, yeah, so. Yeah, with annealing, you can get the desired depth that you want. And like I mentioned, you can model this in like MATLAB and stuff. There's a ton of equations for it.
Man, you guys make annealing look so easy here.
Yeah. Yeah, I'm gonna move forward just so we can get everything done. So then we have thin film deposition for the gate and metal layer. This is for the MOSFET. So this is where we have chemical versus physical vapor deposition. So these are kind of the two main things to know, again, like in an interview.
What is the difference?
What's the difference? Yeah, I got this one wrong. Well, like I just didn't. I mean, I just poorly explained it, like very poorly, and they asked like hypothetical questions. It sucked. But okay, thin film deposits a layer of a material onto a wafer. So this is how you do your metal layers. And so there's two overall methods, which is chemical and physical. So we have physical PVD and CVD are like some of the main ones. And then we have sputtering. Atomic layer deposition is a chemical one. Conventional epitaxy. I don't think I've ever done. I don't know what that is. And then molecular beam epitaxy, which I also am not super familiar with. So for CVD, we're going to use gaseous chemicals, and they're going to be flowed over the surface of a wafer to cause a thin film of material to be deposited on the surface. This method overall produces very flat surfaces, filling in gaps and covering height differences significantly. So you can kind of see here copper on top. A thin gate oxide or silicon nitride is deposited via chemical vapor deposition, and which to act as an insulator between the gate and the silicon.
So
So
why is it done with the chemical vapor deposition versus something like the thermal oxidation?
to it's like good. I don't know like that. Why?
I mean, I can hazard a guess, but
I don't know fully. I don't know. I've never like done a ton of research on it personally. I know a little bit of the basics, but do you know what?
well, it could be because of the quality of the film, but also not sure because I think the interface between the materials could be better if you're doing something like thermal oxidation versus.
Well, yeah, and also we're not like making an oxide layer. We're doing like it's a whole nother.
This process is also typically done under like a vacuum because you need like very tight, or not under a vacuum, but you have to have a very strong control over the gas that's inside of the chamber, and there's typically no oxygen in there.
Right.
So maybe that's why they stated something differently, but in the end, you're still using gas plus heat on top of a wafer to apply layers onto it. So it's basically the same, but it's considered different because one is the total exclusion of oxygen, and the other says, yeah, you can come on in. But that's to my knowledge. I have only read I've only done a little bit of research into these processes, so feel free to correct me if I'm wrong anywhere there.
No, it sounded pretty accurate to me, yeah. Okay, so now we,
The thermal oxidation, sorry, but you do need like some sort of silicon-based material, I think, like already on the wafer, so if you'd already had some other material, like a metal, you can't really do thermal oxidation.
right, yeah. Oh, you just like corrode that material too,
Yeah,
right?
like
Like,
the
'cause
metal probably
copper,
would just go.
yeah, copper just look terrible,
melting,
yeah. Okay, so sputtering is another deposition method is physical deposition. So it uses plasma to break down a sample, which then coats the wafer. This is used for compound coatings a lot. And so, yeah, I mean, you can see the contrast between physical and chemical, as opposed, you're not,
So it's a higher vacuum, meaning it's a more strict vacuum with fewer particles.
I didn't know it was higher vacuum, okay.
Yeah.
Yes, okay, cool,
And
yeah,
then, the main difference is that with chemical vapor deposition, it's more chemical in nature, so the material gets deposited everywhere, even where, like, even in spots that are like not visible to the gas source. And then, in the physical vapor deposition, it's a very line of sight process.
mhm,
So because
That
the
makes sense.
atoms are getting like bombarded and knocked off,
right,
and just like landing, the angle of like the trajectory versus the angle of where the surface is, and like, that it really depends, or I guess it really affects how the film is deposited. So with things like sputtering, you have issues with features maybe like covering up other features.
oh, okay.
If
I
you
got you.
have taller features, it may cause some sort of shadowing where stuff does not get deposited because it blocks the view. So that's just another consideration. Although I think we'll be doing sputtering for the metallization.
I think so too, yeah. Yeah, so yeah, sputtering is definitely
But
what we
there's
do.
an advantage to that in that there's a lift-off process.
Oh, true. Yeah, I
So
mean, we're gonna talk about that
we
next.
take advantage of that,
Yeah,
that property of sputtering in order to not have, basically avoid etching metal.
yeah. I mean, all of these we're gonna go into more Thursday. So I feel like I'm kind of gonna speed through the rest of
Yeah.
them, just because it's definitely past 6 now. But you can also electroplate. That's another way. That's like a way, like a lower cost one. Like I know people do that. It's just like 3D printed materials. They electroplate them for fun. Like you can make jewelry that's like really cheap because of that. Yeah, so I'll just move on. Metal interconnects. This is part of the backend line processing. So like we don't really worry about that for our lab, but it's just something to be aware of. Yeah, and so that's the end of it. It's like covering everything. But does anyone have any questions before we go? And please sign in if you haven't already. Yeah, what's up?
So what is like the industry standard of the thin film deposition? Like which technique do they use at highest levels?
They use all of them.
All of them?
Yeah, it's different parts of the, it also depends like what you're producing. There's like very complex devices that use like a ton of different, like there's, I mean, just huge number of steps. So you need to use a little bit of everything in order to make the final thing, the final product.
Different advantages.
Yeah, so they consider that when they're making, with the process engineers, they consider everything, and it's a full position, so there's a lot to consider for it, so. Yeah. Yeah, so,
There's whole like comparisons you can
Yeah.
draw between each of the deposition or etching. Or,
Yeah.
like all the different techniques.
yeah, so we'll talk a lot more about that Thursday and on everything in regards to like processing, so. Yeah, that's about it, so thank you all for coming. Good to see everyone. Thank you for joining online. We'll post the recording soon. Yeah, that's about it.
Alright. I guess. I don't know if I can ask a question now that
Yeah, go
things are
for it.
over. I didn't want to ask this while we were